Thank you. Dia macam lag sikit. Yeah, okay. Right, so we are looking at exercise 34.1, question 1. Okay, so first question, explain why ethylamine is basic. What is the property of a base, of any base, that we want to look at that makes it a base? So kalau macam acid, we look at the H+, right? For bases, what do we look at? What is it that one thing that we look at in a molecule of base that gives its characteristic as a base? The lone pair, yes, that's right, thank you. So the lone pair, so usually you look out for nitrogen is the most common atom that can act as a base because it has a lone pair of electron. So explain why ethylamine is basic. For 1 mark answer, they only need you to say it contains a lone pair on nitrogen atom. Okay, but I would like to extend that answer that can bond with H+. Okay, so for the mark scheme, as long as you say it contains a lone pair, they should give 1 mark. All right, we don't have to talk about the ethyl group being electron donating, or we don't have to talk about other electron donating or electron withdrawing, because we're not comparing the basicity. So the question is just asking, why is it basic? And just now, as I mentioned, if there is an available lone pair in the molecule, then it can act as a base. It can form a bond with a H+. Write an equation showing ethylamine acting as a base. So you would expect a base to react with an acid. So we've got ethylamine reacting with H+ to form ethyl ammonium ion. Okay, so it's just a matter of adding a H+ to this molecule. Okay, so you have a plus sign here on the negative. So that's why the formula is C2H5NH3+. Okay, if you cannot visualize it, draw it out. Okay, a nucleophile. So a nucleophile is defined as a species that has a lone pair of electrons. So the definition may or may not be the same as the definition of a base, okay? But of course, we need to find a reaction that makes ethylamine a nucleophile. First reaction that you can choose is SN, nucleophilic substitution, okay? Whether it's an SN1 or SN2, and that's my first reaction. It reacts with a halogenoalkane in a nucleophilic substitution of halogenoalkane, which is your AS stuff, okay? In which case, you would have the bromine group in the halogenoalkane being substituted with the amine. Now, again, if you cannot visualize it, draw it out. What type of halogenoalkane? Any one. I'll just choose the simplest one, right? And then what happens is that my amine, NH2, C2H5, will attack, and then this will leave, okay? So that's not the full mechanism, that's just the simplest route. And then I form N, H, C2H5. So be careful. My nitrogen initially has 2 hydrogen, right? But after it is added to the halogenoalkane to substitute the bromine group, or actually it can be chlorine as well. Chloralkane, doesn't matter. Chloralkane, bromoalkane, or even iodoalkane. One of the hydrogen has been lost. Okay, so your product is now CH3 NH C2H5. Okay, so this is the mechanism here for nucleophilic substitution in AS. The other product you need to balance the equation would be hydrogen that you have lost from the amine and the bromine, which leaves as a bromide ion. So it's HBr. Another equation, another reaction is ethalamine reacting with an acyl chloride. Okay, so I'll show you. C double bond OCl. Same thing. If you still remember your addition elimination reaction, okay, this is in topic 33. I will name this addition elimination in A2. Okay. So we have the same ethalamine, C2H5, acting as a nucleophile, acting the slightly positive carbon. One of the double bond breaks, the double bond reforms, the carbon-chlorine bond breaks. Okay, so your product would be CH3, C double bond O, and N, C2H5, and again, there's only one hydrogen left. Okay, so one of the hydrogen has left because your nitrogen would have had a positive charge. It had 4 bonds. Okay, so the product, I really don't have space here. The product is CH3CONHC2H5 plus HCl. Okay, so I'll just put that aside. C2H5 and H2 plus. So you can choose either one, okay? But you need to be familiar with both reactions. Next question is comparing the basicity. Why is phenolamine less basic than ethalamine? This is where we can talk about the electron donating group or electron withdrawing group or any other reasons. Okay, so the reason for phenolamine being less basic is already mentioned in your notes. It has something to do with the lone pair on the nitrogen is delocalized into the ring. Okay, did you mention that? Basically, it's the same reason that you have in your notes. And so this makes the lone pair on the nitrogen of phenolamine less available to accept H plus or to bond with H plus, okay? So please refer to your notes for that. You can also talk about ethalamine, but the question is asking you why phenolamine is less basic. So you have to talk about phenolamine and then comparing it with ethalamine. Well, in ethalamine, there is an alkyl group that pushes the electron density towards the lone pair, making it more available or more attracted to the H plus. Okay, so I will skip that question since it's literally the same as the one in your notes. Next question, alkaloids are naturally occurring compounds that act as bases. Suggest the structure of the product E of the reaction between the alkaloid nicotine and an excess of HCl. Okay, so nicotine here can act as a base. So they already tell you that the phenolamine, well, this is not a phenolamine, but you should already understand that the lone pair on the nitrogen of phenolamine is delocalized into the ring, making it less available. So you can see here, there is an aromatic ring with a nitrogen instead of a carbon. Okay, here you have 5 carbons. So that already tells you the lone pair of nitrogen will not be available to attract H plus because it will be delocalized into the ring. Okay, So the other possible um, basic group would be that nitrogen. Okay? And yes, it has a lone pair. It is attached to CH3. It is attached to a CH2 group here and a CH with other groups attached to it. But we know that they are all alkyl groups. Okay, so alkyl groups pushes electron density, making this lone pair to become available. Okay, now excess HCl, what would the product be? The aromatic nitrogen will not get involved in the reaction, so we just draw it as it is, okay? And the rest of the molecule, the rest of the molecule, except where the nitrogen is, will also stay unchanged, okay? So we said that the nitrogen will gain H plus, making this whole molecule positive, okay? And then the chloride ion is just a counter ion. Okay? Did you all get that? Well, in the mark scheme, they do it like that. It's the same thing. You just write down the positive charge on the nitrogen. And that is the salt that you produce from this acid-base reaction. Okay? So this is an acid-base reaction. Okay. Next, you are converting a phenolamine to a diazonium ion. So the reagents and conditions should also be available in your notes, okay? So I will not go through that. Basically, diazonium ion is unstable. It is derived from or produced from phenolamine, okay? Okay, the diazonium salt is then reacted with a phenol or an aryl amine and in alkaline solution. So just remember that this came from phenolamine. So I'll just add that in, okay? And then the diazonium ion forms an azo group, or it gets involved in a coupling reaction. Okay, how do we recognize this coupling reaction? You look at the phenol and the aryl amine, they call it the aryl amine, where the R group can be hydrogen or any alkyl group, CH3, CH3. They may be the same alkyl group or different alkyl groups, okay? And you notice that in the product, the diazonium ion couples with the phenol and the amine, I'll just call it the amine, in position number 4, at position number 4, okay? Because you all know already that phenol activates 2,4,6. Amine also activates 2,4,6, but they prioritize the 4th position first, okay? So anything that contains alcohol, hydroxy group on a ring, or an amine group on a ring, the diazonium ion will attach itself onto the position number 4. Another thing that I want to point out is that the diazonium ion, which started with a triple bond, now has a double bond only. Okay? Okay. Do you all notice that the bond, the new bond being formed is between that nitrogen and carbon number 4? Do you all notice that? Okay. So that bond is crucial in helping us in the next step. We need to identify where that new bond is being formed. So just remember, new bond formed is between nitrogen and carbon number 4 to either an OH group or an amine group. Okay, so suggest the starting materials needed to synthesize the following dyes. Okay, so here is an alizarin yellow R. Do you see OH group here? Okay, and if we count the number of carbon from that OH group, 1, 2, 3, 4. Can you see that this is the new bond being formed? Okay, so just try to imagine to break that bond, because that will tell you what the starting materials are. Okay, so the starting material on this side would be the benzene ring with an O2 group and the diazonium ion and triple bond and plus. Okay, and the other side would just be benzene ring with COOH and OH. Okay, now the question is asking for the starting materials. The mark scheme allows you to leave the answer in diazonium ion, but the correct answer is the more stable form. Remember, diazonium ion came from the phenolamine. Okay, so we will just use the more accurate and the more accepted answer, okay, which is phenolamine. So this part is the phenolamine part, N2O with NH2. Do you agree? That's the red part, okay? The other part, I will just label it as the blue part, would be the ring with OH here and COOH with a benzene ring. Okay, and that's the answer. The next one, same thing. You've got this NaO3S. We don't know that group. It doesn't look familiar to us. Here, I believe there is a typo. That should be CH32, okay? So please add on the typo. Nitrogen with 2 methyl groups attached to it, okay? So that looks like an amine to me. This one, amine, familiar, right? That amine, okay? So same thing. This is the amine group. So 1, 2, 3, 4. That means my new bond being formed is the nitrogen with carbon number 4. Same thing, I try to break it down. The left side is my phenylamine starting material. The rest of the molecule stays unchanged. So I will just draw them as it is. NH2. And then the other side is the blue side, and that's the aryl amine. And with CH3, 2. Okay? When you tried this question, did you manage to get the same answer? Yes? Okay, good. The diazonium ion is accepted, but it's only other accepted answer, alternatives answer, okay? So I'd rather you go with the most accurate answer first, and then only if you don't remember this in the exam, you just write down the diazonium ion, that's fine, because that will be correct as well. It's just that diazonium ion is not stable. So diazonium ion actually came from the NH2 group. Okay, next question that I want to look at is 3C part 4. Habis sudahkah this? Suggest what effect? Okay. Don't worry about that. We move on to question 3. 3C part 4. This one. Okay. So this is a molecule called the piperidine. How would you expect the basicity of piperidine to compare to that of ammonia? Explain your reasoning. Okay, both of them has a nitrogen, and if you want to draw out that hydrogen bond, you can, but otherwise, if you can see it, then that's fine. Okay, so for ammonia, the nitrogen is attached to three hydrogens. Hydrogens doesn't really have any electron donating or electron withdrawing effect. Okay, as for piperidine, this nitrogen is attached to a hydrogen and there's two other groups. This group is actually a CH2 group, and that is considered an alkyl group. Okay, now what do you know about alkyl group? Electron donating or withdrawing? It donates electrons. It pushes electron density to the lone pair, making the lone pair more available, or we say more electron rich or high electron density. Okay, so what effect does this have on the H plus? Will it be attracted more or less? More. So that means it is more basic than ammonia. To answer that, for how many marks is that? That is a 1 mark. So we say that piperidine is more basic than ammonia due to the electron donating alkyl groups. Yeah, that's all. Due to the electron donating alkyl groups, it's enough. But if you want to add on your answer, it pushes electron density to the lone pair, making it more available for the H plus, that's fine. Okay? Okay, next question, question 7. And a question 7 in it. Yep. Okay. So 1,3-dimethyl which is this one, is a useful starting material. The artificial mask ketone A is a perfume agent added to many cosmetics and detergents. It is made, okay, right. So step 1, we need to look at the changes. Okay, so going from 1,3-dimethylbenzene, the product of step 1, you have added this group that looks like a chicken foot. Okay, so how do you think I can attach that chicken foot onto my benzene ring? What kind of reaction is that? That's an alkyl group, right? Yeah, so that is actually an alkylation. Alkylation. If you look at your, you probably don't have that notes with you now. Alkylation is called a specific name, Friedel-Crafts alkylation, okay? So if you want to attach a CH3 group, you need to react with CH3 and Cl, okay? So here, if I want to attach that chicken feet or foot to the benzene ring, this means that I need that group to be attached to chlorine as well. Okay? With the presence of a catalyst, AlCl3, so that this catalyst will take off that chlorine to give me an electrophile with a positive charge there. So then the benzene ring can attack. Okay? That's the thing about alkylation and acylation actually. It needs to be the alkyl group attached to a halogen, chlorine or bromine. And you need a catalyst. That catalyst needs to match whatever halogen you have attached to that alkyl group. If it's chlorine, AlCl3. If it's bromine, AlBr3. Okay, so that's step one, alkylation. Step two, what have I attached this time? C double bond O CH3. What group is that? C double bond O with the CH3. What group is that? Yeah, I know it's a ketone, tapi if it's like, can anyone identify that group? C double bond O with a CH3 is an acyl group, okay? Yes, you are right, it is a ketone, but it's a ketone because if it's got C double bond O to both carbon. If it's a hanging bond here, then it's just an acyl group, okay? So same thing, acylation, you also need whatever you want to attach must be attached to a chlorine, and then you need a halogen carrier. So if we look at this question just now, if you want to attach C double bond O CH3, that means you need to use C double bond O CH3 attached to a chlorine. Okay? It must be attached to a chlorine or a bromine, halogen, the halogenoalkane or halogenoacyl version of it. Okay? So that's step one, step two. Step three, what have we attached now? The nitro group. And so this is called nitration. Okay? So I will just help you with that because once you know the reaction, this one is acylation, Friedel-Crafts. So Friedel-Crafts can be alkylation, acylation, right? The rest of the questions, you should be able to answer them. Okay, reagents and conditions, that's just straight off copy from your notes. Part 4 suggests the structures of the two products formed when A is reacted with an alkaline aqueous iodine. Does anyone remember that reagent? Well, there's only one reaction from your AS that reacts with alkaline aqueous iodine. Yes, Nina? Iodoform reaction, yes. Iodoform reaction. Do you remember the criteria for an iodoform reaction? You need to have a CH3 attached to... Yes, you're right, CH3, tapi what must it be attached to? CH2 next to... Because there are many CH3 here. This is a CH3, this is a CH3, 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 CH3. So which CH3 will give the positive result for iodoform? Can anyone see it? The CH3 needs to be attached to C double bond O. That's right. Okay, so this CH3 needs to be attached to C double bond O in order for a positive iodoform reaction. Okay, so I don't remember your notes from the AS, but I will just tell you the answer. What happens during the iodoform reaction is that the CH3 will fall off to form triiodomethane, which is CHI3, if I'm not mistaken, where 3 of the hydrogen has been substituted with an iodine. triiodomethane. Do you still remember that? Does it sound familiar? CHI3, okay? So that's why you need the CH3, because they will form CHI3, which is called the triiodomethane. Please refer to your AS notes for this. And the other product is this part, okay? It forms a carboxylate. Actually, I also don't remember that reaction, but O minus, and then the rest of the molecule stays unchanged. Then we've got an NO2, NO2, and that chicken foot. Okay, so please refer to your AS notes for this reaction. Okay. The next question. The other parts of question 7, is there anything else that we can do? Polymerization, you haven't covered polymerization. Okay, so we can skip part B of question 7. Next, we're going to look at the last question for today, question 13. Okay, so again, we look at the different basicity or the base strength of S, T, and U. Okay, so these are all nitrogen-containing compounds. Okay, so I'll just quickly draw them out. C6H5, this is an amide, C double bond O and H2 with a C6H5, which is a benzene ring. So that's S. And then T is phenolamine, C6H5 and H2. I will draw the lone pair because all of them has a lone pair. And lastly, I have a benzene ring, C6H5, attached to a CH2 and H2. Okay, so they all have the benzene ring. But what's most important is we want to look at what group the nitrogen is directly attached to. Okay, what it is directly attached to rather than the whole molecule. So for S, the nitrogen is directly attached to C double bond O. For T, the nitrogen is directly attached to the benzene ring. For U, the nitrogen is directly attached to a CH2 group. Okay, so you can see that only in T, the benzene would have an effect on the lone pair of electrons. Okay, whereas in S and U, the benzene rings are not directly attached to the nitrogen, so they don't have a lot of effect there. Okay, the easiest one to see is U. Why? What is the effect of the CH2 group? It's an alkyl group, so alkyl group, electron withdrawing or donating? Electron donating group. Okay, so it pushes electron density, making the lone pair of electrons to be the most available. Okay, so electron donating. So the electron density of the lone pair increases. it will attract the H plus the best. So this is the most basic. Okay? U is the most basic. And then we have S and T. S, what functional group is that? C double bond O and H2. Do you remember what is the name of the functional group? C double bond O attached to an NH2 group. C double bond O and H. Amide. Okay, so just like your peptide bond. And amide is neutral. It is not basic at all. Okay? There's a lone pair there, but because it's not a base, it must mean that the lone pair is not available. Okay? Now, what do we know about C double bond O? Is it electron donating or electron withdrawing? It is electron withdrawing. The hint is that oxygen there. Okay? Oxygen is electronegative. It wants electrons. It wants to take away any electron density around it. Okay? So this lone pair of electrons on nitrogen will be taken away or will be withdrawn by the oxygen, making it less available. Okay, so if it's less available, then it cannot attract or bond with H plus. Okay, so amide is actually the least basic here. Okay, so we call that, do they describe and explain the, okay, so the amide S is the least basic, and T, phenolamine, is in the middle. Okay. Now in T, the lone pair is also less available because it is delocalized. It forms a part of the delocalized system. Okay. Delocalized system is actually just inside the ring, but because the lone pair of electrons sits in an orbital that is also in the same direction or parallel to the p orbitals of the delocalized system. So now it is extended. Okay, that's a bad drawing. But we say that the lone pair of nitrogen in T is now being delocalized into the ring. Explanation for 3 marks. Okay, let's see. U is bigger than T is bigger than S. Yeah, correct. Okay. So first we can say who's the easiest one to talk about? U, I think. U is the easiest one, right? So we can say that U is the most basic because electron donating alkyl, cannot spell, alkyl group pushes electron density to the lone pair. Therefore, can accept H plus or more able to accept H plus. Since we're talking about the relative, more able to accept H plus. Then we talk about the phenolamine T. For T, the lone pair on nitrogen overlaps with the high delocalized system, making it less available to accept H plus. And lastly, S in S electron withdrawing group of C double bond O makes the lone pair on nitrogen to become unavailable. Okay, so completely unavailable. Bukannya less available, but this time it's completely unavailable to accept H plus. Okay, so that's how you would answer basicity or comparing different basicity of two or more compounds or molecules. Okay? All right. Nina, can you please stop the recording? Before you go, please collect a paper 5 for you to do over the long weekend.